Hello everyone and welcome to another episode here on the School of Quantum YouTube channel. Today we are looking into Toshiba quantum technology, and if you are interested in what Toshiba's future in terms of quantum is, what they are looking into and what their investment into the quantum computing future looks like, then stay tuned for today's video because we are diving deep into Toshiba quantum technology. And with that, let's hop right onto their website. Oh, as always, make sure to get yourself something to drink, right? And looking at their website, what we see is this little video animation here with QKD, PQC. So we are seeing we are in the quantum communication realm. And here it says Toshiba Quantum Technology securing our quantum future. At Toshiba, we are committed to delivering world-leading technology that protects the private information of citizens and organizations. As quantum computing becomes more widely available, the volume and severity of cyber attacks will put sensitive data under threat like never before. Only quantum secure solutions will be able to withstand decryption from quantum computers, which will have the power to bypass current encryption methods in minutes. Our quantum cybersecurity solution, based on decades of scientific research, apply the fundamental laws of quantum physics to deliver provably secure network communications that will remain resilient even in the age of quantum computing. And this is, of course, again relating to this idea of harvest now, decrypt later. So, and the idea of course, the quantum computers being able to crack today's encryption processes. So, encryption works based on prime numbers and on prime factorization. Quantum computers are much faster than classical computers in solving this problem. This has been figured out originally by Peter Shor with the Shor algorithm, and that led to this idea of the harvest now, decrypt later concept, where today, if you are let's say a malicious actor, you would be able to hack into somebody's communication channel and just listen to the encrypted communication and copy the files or copy the communication somewhere, to then later on use a quantum computer to hack this encryption. And this, of course, is not relevant for every single piece of data. So if you are looking at, I don't know, the authentication app that you have on your phone, and you have to put your number from the phone into the browser, and then it's being, let's say, encrypted and communicated with the web service that you're trying to access. This is not relevant because after a couple of minutes this key will expire. So right now we don't have quantum computers that can hack this, so probably this is not an issue. However, if you have some information that is classified that needs to be protected, for example medical data over your whole lifespan, we don't really know what will be the day where a quantum computer can hack today's encryption. So in these cases, it might be relevant to actually have some encrypted communication that cannot be cracked later on by a quantum computer. And this is what I think Toshiba quantum technology is looking after. And now let's see what the concrete solutions are and what else they have to say, right? So we are quantum security pioneers. Toshiba has been at the forefront of quantum computing technology since 1999. Our solutions underpin the world's first quantum secured metro network, and we've created a quantum secure communication platform that makes existing data carrying networks safe from attack by quantum computers without any compromise to performance. We've achieved a series of world firsts in quantum technology deployment, developing quantum secure and future-proof network communications infrastructures that can protect data from any threat, even those posed by quantum computers. Then we see that there's a news section down here. I'm recording this in March 2026. I'm not sure. Yeah, here we see there's a press release also from 2026. So this is pretty much up to date. Latest one, Toshiba enables global connectivity for quantum safe networks with bridging solution. And then here in the United Kingdom. And then there's some more stuff down here, case studies, white papers, resources, and also some LinkedIn posts. Here you can see March 2026. So pretty much up to date with two very well-known faces in the community of quantum communication, which is Charles Burnett and Gilles Brassard, who are at the very forefront of developing these quantum communication protocols here, pioneering work on the BB84 protocol. Okay, and then down here, I guess we have the different components. So there's the quantum key distribution part, quantum key management, and then the quantum safe telecommunications. And I guess we will go on into these a little bit more detail a little later in this video. So Toshiba Quantum Secure Networking in action. We see here BT and the HM government are already posting their information here on the website. Okay, and then there's a call to action to get in touch. Now let's look at the quantum secure networking tab here. So there's the long distance QKD system LD, the multiplexed QKD system MU, and some resources, as well as the quantum key management. Let's start with the quantum key distribution first. I want to stay on this side. So quantum key distribution, delivering provably secure networking for the quantum computing age. Cybersecurity threats are increasingly rapidly, particularly the threats posed by quantum computers. Yes, that's what we know. And then here, benefits of quantum key distribution, deployable today, providing quantum safe security regardless of an adversary's computing power, capable of detecting and mitigating eavesdropping attacks, and then prove secure and immune to future developments in mathematics and computing. That's maybe also important to point out, right? If you're using this quantum key distribution scheme and the quantum communication, that's exactly what it says here, right? So it is not only it's not only proof against eavesdropping, right? It is provably secure and immune for even future developments in mathematics. So even if, for example, somebody figures out how the prime numbers work, it is still safe. It is secured by or governed by the idea of quantum mechanics, the non-cloning theorem, and the entanglement and superposition that are core fundamental concepts in quantum mechanics. And if these are, let's say, remaining correct, and there's always the falsification idea, right? But as long as quantum theory stays the most accurate theory of the microverse that we have, these mechanisms, they are basically going to protect the communication. And you can be able to also then detect if somebody's trying to eavesdrop, because that person would try to copy quantum information, which is not possible protected by the non-cloning theorem, right? And that means that basically you can identify that somebody's trying to do that, and then, for example, stop your communication. Okay, now there are these two different systems that we've seen already before, the LD and the MU. Let's quickly take a look into those as well. So there's the long distance QKD system LD, ensures quantum secure networking over distances of 93 miles plus, optimizes CapEx, capital expenditure, with fewer systems required to meet your distance needs, and then proprietary active stabilization technology that adapts to the network environment. So that's also something that we've seen before, right, with other players in the quantum communication market. It is not enough to just take an existing fiber or even have a new fiber, put it somewhere in the ground, and then start your communication. You also need to actively stabilize this. So after a while, you need to tune things. I think the polarization might be shifting over time of your fiber, and hence also your photons. So you kind of need to correct for that over the course of time. And that's what you need to get, let's say, such a communication scheme to work above a couple of hours. Then on the other side here we have the multiplex QKD system MU, developed to deliver QKD in complex metro scale environments with the simplest integration, provably secure protection provided by the most advanced QKD protocol, and then proprietary active stabilization technology that adapts to the network environment. We've seen that before. Then, here's again some note on the 2 decades of research and the 1999 groundwork. And then down here we also have some, let's say, basic frequently asked questions in the context of quantum key distribution and quantum communication, which I will not go into detail now. Let's zoom into those 2 different technologies. So the long distance QKD system LD. Quantum computing is threatening to render public key encryption techniques insecure, with data in transit particularly vulnerable to attack. QKD provides the answer, enabling quantum-safe cryptography across fiber networks. Development of long-distance QKD technology has been a significant challenge for manufacturers, as the quantum signal decreases in strength exponentially as fiber length increases. And maybe a quick zoom out here. Why is this so critical? Why is this so relevant? Because if you are using quantum key distribution, you are basically relying on single photons. So you cannot just easily make the light source brighter, because photons are, let's say, at the very lower limit. They are the quantization of light. There's no smaller unit than a photon, which basically means you're operating on the smallest units, and if one of those, for example, gets absorbed by the fiber, then it's gone, right? So your signal is gone, and that's what makes it so challenging, what makes it so hard, and that's why this exponential drop in terms of fiber length is a big issue. Okay, so the LD system overcomes this challenge. It uses Toshiba's unique patented technology to ensure exponentially high secure key rates over distances of 93 kilometers or more. Deployed using a dedicated QKD fiber, the LD system also offers simple setup, auto-alignment, and real-time optimization. This combination supports a greater number of demanding use cases and reduces CapEx, as fewer QKD systems are required to provide quantum security over long-range connections. It also reduces business risk by offering sufficient capacity to support future network demands and even enable older degraded fiber to become quantum secure. It's high performance quantum security over the long haul. Okay, and then we have some highlights here. So ensures quantum secure networking over distances 90 miles plus, and I think that is probably, let's say, the USP here. Right now these techniques, they are limited, and you cannot just scale them up to infinite length. You will always need another node and another node roughly after every, I don't know, 100 kilometers. So 90 miles is already quite a step up, and that's probably the USP here. Optimizes CapEx with fewer systems required to meet your distance, because I guess it is more expensive to install and maintain one of those systems in your network rather than putting a longer fiber, right? Fiber maintenance and price is probably cheaper. And then proprietary active stabilization that adapts to the network environment. We've seen that before. I talked about that before. Okay, so here it also says using high performance C-band technology with a superior optical loss budget 30 dB, LD overcomes the traditional problem of quantum signals weakening over longer fibers, ensuring long-range quantum safe networking while optimizing CapEx. So the C-band is one of these typical communication bands. I'm not an expert in that, but there are different bands that have historically been used for various different reasons. It has to do with the light sources, so the lasers that were available. So these bands, they are basically the color bands, right? We are usually in the infrared range because the absorption is very low. And usually those fibers, they have been operated in ranges where you had the lasers available and the fibers available. And by the time these bands, they have been added in order to put more load, to have more data going through your communication infrastructure. And I mean, initially those fibers in telecommunication, I think they started very much when we had the first intercontinental, like below the sea lines that were being used to connect the continents in terms of internet connection. That were like the first bands, and then from there things were like branching out. Here we see also again this remark to the BB84 protocol, which is this protocol used in quantum key distribution. And then there's some notes here on how safe and stable everything is, but we are not going to go into the details of this now. And then let's quickly check out the numbers down here, but I'm not actually going to read the whole table to you. Just to say, so it is in the C band, which is this 1550 nanometers infrared wavelength. It is using the T12 protocol, which is an efficient BB84 protocol with decoy states and phase encoding. We've talked about the loss before. It allows for a range of 93 miles plus. And then there's some other stuff down here. But yeah, I'm not going to go into the details, just to say, so it's a 3U height, 19-inch rack mount system. So it fits into classical telecommunication racks and can hence be used in the classical data center / communication center setup. Now on the multiplex QKD system MU, so I think we see the same kind of proposal up here. So quantum computing is threatening to render public key encryption techniques insecure with data in transit, particularly vulnerable to attack that we've seen before. And QKD is the answer to that. QKD normally requires separate dark fibers dedicated solely to carrying quantum signals, but with Toshiba's multiplex QKD system MU, you can easily integrate QKD onto existing data carrying fibers and without any compromise to performance. And that's kind of where this system is separating itself from the other one, right? In the previous one, we had used this specific fiber here and only use it for quantum communication and use it with this specific wavelength. And then you can go up to 90 miles and plus. Here in this case, the value proposition is a bit different. It is use an existing fiber that you already have somewhere between two nodes, and without any issues of, let's say, having it even used for normal data communication, you can put the quantum stuff on top of this. So without any compromise to performance on the other channels, you just put the quantum key distribution on top. So deployed over an existing single fiber or a fiber pair, the MU QKD system uses O-band WDM technology to overlay quantum signals with network data, eradicating the need for an additional dark fiber. So now we are in the O-band, which is a different band again in terms of color of the light and the infrared spectrum that you're actually using. This true coexistence between QKD and data dramatically reduces the CapEx and OpEx costs involved in delivering quantum-safe encryption with simple setup, auto-alignment, real-time optimization, and high key rates. Multiplex QKD system MUs and ensures operators are set to deliver QKD across the networks. And I mean, here you also kind of see that they understand, let's say, the different aspects that the telecommunication providers look out for, which is not a surprise because I guess Toshiba has been active in this before. They know that the operators are looking at the capital expense and the operational expense of their networks because these are the main cost drivers in the telecommunication, I guess. And they kind of know how to target that audience and probably also know how to cater or how to deliver to these players, right? So here we now see developed to deliver QKD in complex metro scale environments with the simplest integration. So these O-bands, as far as I understand, and I'm not an expert on that, they're usually kind of added bands in spaces where you have a higher density of data going back and forth, like for example in a metro context, right? Like in a city where you have multiple different let's say fiber branches going out to all of the office buildings and the company consumers and whatnot. So this is a more dense network, so you need more and more channels to go on top to communicate all of this data. And this is where you want to have additional bands so that you can actually run multiple channels at the same time via a single fiber. And that's also where this becomes interesting then. Provably secure protection provided by the most advanced QKD, and then proprietary active stabilization technology that adapts over the network environment. I think we see the same or similar stuff as before. So quantum secure networking with easy integration. Toshiba's MU system reduces the CapEx costs and complexity of deploying QKD by eliminating the need for additional dark fiber. Using WDM, MU enables QKD signals to coexist on fiber carrying multiple 10 GB per second or 100 GB per second classical data channels by multiplexing the O-band QKD signal with C-band data services. So that's basically what you see here, right? So you have the C-band, the infrared band that is being used that we talked about before, right? That keeps on going for normal kind of data distribution. And then you're using this O-band on top, so different color of light to do this quantum key distribution and then basically multiplex. And I think the rest is similar to what we've seen before. Here it also says O-band, which is running into which has a wavelength of 1310 nanometers. That also makes the distance a little bit shorter. So here we see it's only 56 miles plus distance. And again, it comes in this rack size that you can mount into your existing telecommunication system setup. Then there's also the quantum key management. I will very briefly skim through that. So the quantum age demands quantum secure networking. Without it, even the most sensitive transmission could be decrypted by quantum computers within minutes. Quantum key distribution is the technology that underpins quantum secure networks. This uses the quantum properties of light to generate quantum secure keys for encryption and decrypting data. Quantum secure keys need quantum specific key management, so cryptographic key management systems are the foundation of the most online data security, responsible for routing and delivering the secure keys with secure encrypted data transmissions. Quantum key management systems are specifically designed to manage and route quantum secure keys through QKD networks, enabling them to be shared reliably between parties. And then here are the benefits. We've talked about these before. Let's see what else we have here. So again, the note on the two, and some frequently asked questions. Let's quickly look at the system that they are actually selling, the QKMS, Quantum Key Management System. In here it says compatible with QKD systems from multiple vendors. Toshiba's Quantum QKMS can manage secure key distribution throughout QKD networks. It offers a highly flexible approach to building quantum secure networks, QSNS, enabling network operators to easily manage and add QKD functionality to their secure communication applications. The Toshiba QKMS is the simple route to robust quantum security. So secure key routing mechanism allows the distribution of quantum keys between any two network QKD systems trusted nodes. Simple integration into your network with REST-based key delivery API compliant with ETSI GS QKD 014 industry standard. So REST-based API is basically basically application interface, and REST is a specific methodology that is nowadays used in almost all relevant API systems. It is basically behind all of the apps that you're using when you have a browser and in the back some server that is running the application. This ETSI GS QKD014, I don't really know, but it says it's an industry standard. So we believe that for now. Future-proof design to work securely alongside QKD systems, delivering secure key rates exceeding 10 megabytes per second. And then down here, there's a scheme that is explaining it. So easy flexible deployment. The Toshiba QKMS abstracts the key delivery layer from the physical layer, resulting in a logical key delivery overlay system. This provides flexibility and on suitably deployed networks enables features such as key rerouting. So I guess now let's say you have this physical layer, right? We've seen the systems before. So you have the QKD systems that are producing those entangled photon pairs that are distributing those keys across the network. And now you have an application layer sitting on top, right? And it might be, I don't know, different applications that demand secure communication. And my understanding for now is that basically this other type of systems, they sit on top of that. So they're basically actively managing those keys that are permanently being generated and enabling the applications to access this secure key ability, right? So you see here you have the QKD systems with the physical nodes down here that are routed in some type of network architecture and are distributing keys now along this network. And then on top of that, you have this encryption key service layer sitting on there that is basically managing those keys, so collecting those numbers, and then via a delivery API is then kind of delivering those encryption keys and also the decryption mechanism, right, to the users, which can be corporates, which can be governments, which can be private people. And it says encryption key for end-to-end encrypted communication. So that's then basically delivered both for the encryption and then also for the decryption on this service layer, which sits on top. It also mentioned up here that this is agnostic to the provider of the QKD system. So I guess that's really like sitting on top in the software layer in a way. Good. Quickly on the industries. So which industries are targeted here? We see telecommunications industry is the main user of this, which kind of makes sense. I don't know if it says something here about the industries that telecommunication is catering to. No, there's just a lot of Q&A down here. Besides that, there's this Insights tab, Quantum Insights, so Toshiba Open Session 2022, the future of the quantum economy, and so on and so forth. I think this is probably not extremely interesting. Let's quickly check out the About Us part, as always at the end of each video, right? So we are at the cutting edge of innovation in quantum technology since 1999. We've achieved a series of world firsts in QKD development and deployment, harnessing quantum physics for future-proof network communications infrastructure. We've seen that before. What is QKD? 2 decades of research, latest research articles here that might be interesting. So on the heritage, how it began in 1999, we started research into quantum cryptography at the Cambridge Research Laboratory of Toshiba Research Europe Limited. In 2003, we were the first to announce quantum key distribution over 100 kilometers of fiber. In 2008, we had collaborated in the first QKD network in Europe as a core partner to the EU-funded SECOQC project in Vienna. Since then, we've continued to advance our technology, increasing the range and secure key rates of our systems, and developing a QKD solution that can be easily deployed on existing in-use fibers. We are consistently breaking our own records and those of the broader industry. And then today, so we have QKD system suitable for a range of communication networks, and that are the ones that we've seen before. Quantum cryptography in action, so that might also be interesting. Our Toshiba QKD systems have demonstrated and deployed successfully around the world. Working with JP Morgan Chase in Columbus, Ohio, we demonstrated that QKD can be used to secure blockchain communications. In Graz, Austria, we demonstrated protection of medical data in transit, and REST in a trial with Austrian Institute of Technology as part of the OpenQKD project. In partnership with BT in 2021, we successfully implemented quantum security of smart manufacturing data shared between the National Composite Center and the Center for Modeling and Simulation. The deployment allows industrial organizations to secure, transmit, corporate IPR and other sensitive information between the facilities instead of having to rely on transportation via physical portable storage devices. We launched London's first secure metro network with BT in 2022. This award-winning quantum trial connected sites in London's Docklands and the City and the M4 corridor for end user EY. A complex network with multiple endpoints. It's paved the way for commercial QKD services in the UK and beyond. Watch the full video and so on. So has already been deployed in that sense. And then what's next? So there's some industry debate concerning when quantum computing will become available, but whether it's 2, 5 or 10 years from now, there's work to be done to ensure the continued security of our data. As the field of quantum technology continues to evolve, we are always expanding and developing our areas of research and innovation. We are working on ways to implement QKD via satellites, which would make QKD networks more stable while increasing security and reducing cost. Meanwhile, the drive for large-scale deployment will create a need for chip-based QKD devices that enable greater accessibility and enhanced functionality. We are also working on projects such as twin field QKD, which will significantly increase the transmission range without the need for quantum repeaters. And inspired by quantum technology, we are also launched a simulated bifurcation mechanism SQBM Plus solution and an innovate quantum inspired algorithm and corresponding quantum solution for solving complex problems and making optimal decisions in short time spans. At Toshiba, we put innovation first. Our extensive historical and ongoing R&D activities ensure we are ready to deliver quantum secure solutions suitable for a global mass market, and our provably secure quantum solutions can protect communication networks today, tomorrow, and into the future, regardless of advancements in quantum computing. And I think there's a lot of stuff in here. So we see there's this aspect of looking into satellites. We've seen satellites with other companies already that are also active in this field of quantum key distribution and quantum communication. So if you haven't seen those videos yet, check out the Hidden Quantum Champions playlist. There are also other things in here which are very interesting. So there's this chip-based QKD, which is like chip-based optics, also very, very interesting and active field right now. And there's also other things like this twin field QKD, which will hopefully then allow them to go even further, even longer distances, because this whole field of quantum repeaters is actually not easy, because you cannot just copy the information and then repeat it, right? So that's a whole nother story in itself. And then, there's also research on the algorithms and so on. So quite a lot of stuff to be done at Toshiba. Generally, like zooming out, I think it's a very interesting and active field. I think it makes sense for Toshiba to look into that. And it's also kind of, let's say, a good bet, right? Because even if the quantum computers will take us a long time, this is something where there can be business generated already today. It's a bet on whether regulation will enforce that, whether companies are becoming more skeptical about the, let's say, about the encryption mechanisms and the safety of their data, especially the highly IP related data, right? So this is becoming more and more of a topic, and as it becomes more and more of a topic, it also becomes more and more of a market, so there's a growing demand, and we will see this even before we see the quantum computers taking off, right? Because once the quantum computers are coming closer and we see that we are getting closer and closer and closer to this point where they can actually decrypt data, people will already want to have these safe communication channels. So I think it's a very interesting bet. I would also be interested into your opinions on that. So let me know down in the comments below. If you like this video, make sure to subscribe to the channel. I'd be very happy to see you in the next video again. Until then, bye bye.